G'day guys, a couple of students of mine have asked for a bit of a refresher on differentiating vector functions. So I thought I'd give an example, but before we do the example, I thought we'd just go back and define a vector function just so our knowledge base is quite solid, and then we'll go and use that knowledge to get hopefully an intuitive understanding of why or what we're doing when we differentiate vector functions like this one here. So hopefully you guys are already aware that a vector function is a mathematical relationship of one or more variable, in this case t, whose range is a set of multidimensional, in this case two, I and j, vectors. So we know that the domain of a vector function, or the domain of a vector function, I don't know if you guys know it, but the domain of a vector function is, in this case, any value of t for which the components I and j are defined. So in this case, any value of t that we stick in here, be it positive or negative, will give us a defined value of I and j. However though, if we were to say on the fly here, if we had a vector function r of t equal to 1 over t squared minus 4 I plus, I don't know, 6 over t squared minus 49 j, this vector function, the domain of this would be all real numbers of t except for plus or minus 2 and plus or minus 7, because for those values, the components of this vector function, I and j, for plus or minus 2, the component I isn't defined. And for 7, plus or minus 7, sorry, the component j isn't defined. So that's a little bit of an example of where you'd get, domains which aren't just all real numbers of t. So basically what we can do is from here, we're going to use that definition that I came up with, or just, the one or more variables whose set is a range of multidimensional vectors. So what we've got here is we can define that, a vector function, as just a function. We're going to, like a function which acts as a component for a one-dimensional vector, I. And in this case, we're going to have two dimensions, so we're going to have two completely different functions, and that is the component for the vector j. So you can see here that this is the sort of the basic sort of definition, or the way that we can describe a vector function. Another way that some people might like to write it is we could write it as r dash of t is equal to f of t g of t. So in this one here, what we've got is the fact that we have f of t first. The implication is that this is the component for the vector I. So these are just two different types of notations that we could use. Now, as I said before, in a vector function, the components of the overall function R act independently of each other. In this case, we have the component for the I vector is acting in this direction, and the component for the j vector, or the positive components anyway, is acting in this direction. So basically, they don't have any effect on each other, and as a result, what we can do is we can differentiate them separately. For example, if I was to use this notation here, and I was to find the derivative of this r function, so we've got r prime of t, the way that we would find the derivative of this is we would simply just differentiate each of the components separately. There's no black magic. It's just we just find the derivative of the component of the vector I, and we find the derivative of the component of the vector j with respect to t in this case. Now, if we were going to apply this to this function up here, let's just have a go at doing that. So the example function, let's do it. So we have r of t is equal to cos of pi ti plus sine of pi tj. Now, hopefully you guys are aware of the chain rule, because we're going to need to use the chain rule here. So the derivative of this function, r dash of t, don't forget my arrow, is equal to the derivative of cos, which is negative sine, times the derivative of the inside, which is just pi. And then we can multiply it by I. Plus the derivative of the second part, the derivative of sine is just cos. And the derivative of pi t, like the first one, is just pi. And we're going to multiply that by j. Now, textbooks would probably like you to make this look a bit nicer. So to do that, what we're going to do is we're just going to take the pi and move it out the front. So this is going to be equal to negative pi sine of pi t, and that's for the component vector I, plus pi times cosine of pi t for the vector j. And that is our derivative with respect to t. Cool. Now, the question asks us for the second derivative as well. Now, like the first derivative, in this case this one, we can write the second derivative. Let me just make myself some space. The second derivative double dash of t, like the first derivative, we're just going to differentiate the components again individually. So this is just going to be f double dash of t I plus g double dash of t j. So bring it down to our question. So we're going to have to just differentiate this part. So again, the derivative of sine is cosine. So we're going to have this, the double derivative, double dash of t, is equal to negative pi, because that we can just put that out the front. Derivative of sine is cosine. Cosine of pi t, and then we're going to be multiplying that by the derivative of the inside, which we know is just pi. Now the derivative of cos is negative sine, so I'm going to make this a negative rather than a positive. We'll put that pi still there. And then the derivative of the inside is just pi. Now, I've forgotten to put the I in. And that's multiplied by the vector j. So again, we can, like we did with this one, we are going to simplify it or fix it up, make it look a bit neater. So we have the r, the double derivative with respect to t, is equal to, we can take the pi to this pi to the front, and we're going to have negative pi squared cosine of pi t I, and that's going to, then we're also going to take that to the second line. I've run out of space. minus, take this pi to the front, pi squared sine of pi t j. Cool. So that's the simplified version of it. So basically what have we learnt in this little video? Well, we've learnt that a vector function is just a mathematical expression whose variables have an output of multidimensional vectors. So basically what we have here is our variables f of t and g of t. They're the output of each of these are the coefficients on the vector in the I direction and the vector in the j direction. As a result, we know that the vectors work independently of each other, and as a result, we can differentiate them independently. Once we differentiate them independently, the differential that we get, the vectors are still independent of each other. So if we want to find the double derivative, we can again differentiate the vectors independently. So as a result, the differentiation of vector functions is not that complicated. It's when they get a little bit obscure, or you might have to do a little bit of multivariable differentiation where it becomes a little bit more tricky. But in these sort of basic examples, you shouldn't have too much trouble. So guys, I hope this rambling video helped a little bit. If it did, throw it a like, hit subscribe to my channel. I put out videos all the time. But until next time, I'll see you guys later.